We are in Topic 3, Introduction to Statistical Inference.
Imagine you've developed a new flu vaccine. Before it can be distributed worldwide, you need to know if it actually reduces infections. To get a flawless answer, you would have to test every single human being on Earth simultaneously. That is a physical, logistical, and financial impossibility. Because scientists cannot measure entire populations, they rely on sampling. They extract a small, manageable, and highly representative fraction of people, say 1,000 volunteers, and run the trial on them. We use the traits of this tiny subset to guess the traits of the entire planet, which means every piece of data we base our decisions on is, by definition, incomplete. Let's say your trial finishes, and the results look promising. The group that received the vaccine had 7.4% fewer flu cases than the group that received a placebo. But there's a catch. When you're looking at a small group, random chance can easily create illusions of success. Statisticians call this sampling error. If you flip a normal coin 10 times, you might get 7 heads. Scientists must prove this 7.4% drop represents a real effect, rather than the medical equivalent of flipping 7 heads in a row. To bridge the gap between that small trial and global reality, scientists use a rigorous mathematical framework called statistical inference. Your trial gave you a specific number, 7.4%, but the odds that a sample's exact point estimate perfectly matches the entire 8 billion person population are practically zero. This chart shows the distribution of sample means. Because that single point estimate is unreliable, statisticians calculate a confidence interval. This gives us a range of values where the true reality most likely exists. The math expands our precise 7.4% estimate into a wider boundary. Looking at these outer brackets, we can guarantee with 95% confidence that the actual effect of the vaccine across the entire population lives somewhere inside this shaded zone. This interval calculates our margin of error. However, knowing the range of possibilities doesn't definitively prove the vaccine outperforms a sugar pill. We still must test the result against a skeptical baseline. That baseline is called the null hypothesis. It is the strict assumption that your vaccine does absolutely nothing at all. Before they can accept a discovery, scientists are required to play devil's advocate. They operate under the assumption that the difference in sickness seen in the trial was likely pure random chance. To test this, they calculate a p-value. This is the exact probability of getting your trial's results, or something even more extreme, if the null hypothesis is completely true. The p-value is the ultimate trial by fire. It acts as a strict noise detector, calculating the precise likelihood that a medical breakthrough is nothing more than a statistical fluke. This brings us to the level of significance, or alpha. The global scientific standard draws a firm line in the sand. This risk threshold is set at 0.05, or 5%. Let's run a scenario. The trial data is processed, and your calculated p-value comes out to 0.09. That means there is a 9% chance the vaccine's success was just luck. Because 9% crosses our threshold of acceptable risk, regulators like the FDA fail to reject the null hypothesis. The drug is blocked. Now, look at this bell curve, highlighting a different scenario. Here, the trial yields a p-value of 0.01. This tiny yellow region in the tail shows there is only a 1% chance your result was a fluke. Because 1% falls safely under that strict 0.05 threshold, the evidence is strong enough to reject the baseline assumption. Scientists can officially declare the vaccine's effect to be statistically significant. But there is a harsh reality built into all of this math. Statistical inference never provides absolute 100% certainty. Even with a stellar p-value of 0.01, we still face what statisticians call a type 1 error, or a false positive. There remains a lingering 1% chance that the drug does not work. These tools function as mathematical filters designed to quantify the noise in our data so we can manage the risk of reaching a false conclusion. We can't measure everyone, and we can't eliminate the unknown. But confidence intervals and p-values provide the mathematical language humanity uses to make world-altering decisions, while keeping the odds of success in our favor.
Disclaimer: Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement, while all academic content has been reviewed and guided by the instructor.